Hi guys, welcome to a lesson of partial differential equations. So in today's class, we are going to discuss the problem of heat equation. In fact, non-homogeneous heat equation with time-dependent boundary conditions. And we will use Duhamel's principle for the Newman conditions. So let's take a question. Ut is equals to alpha squared uxx plus cosine 3t, and the boundary conditions are ux of 0 comma t is equals to 0 and ux of 1 comma t is equals to 1, and the initial condition is ux comma 0 is equals to cosine pi x plus 1 over 2 x squared minus x. All right, so we can see that this is a non-homogeneous heat equation with non-homogeneous boundary conditions. So now, first of all, we know that for this type of problem, the solution ux comma t is given by wx comma t plus vx comma t. And if you remember that wx comma t, in this case, in the case of Newman non-homogeneous boundary condition, is given by b minus a divided by 2l times x squared plus ax plus alpha squared b minus a over l times t. All right, so in this case, this is b and this is a, right? So we can write here 1 minus 0 divided by 2 times L is equals to 1 here. 2 times 1 times x squared plus, and a is given as 0, so 0 times x plus alpha squared is given as alpha squared times again b minus a divided by L times t, right? So now w of x comma t is equals to x squared over 2 plus alpha squared t, right? So this is w of x comma t. Now the problem is reduced to this, right? And we know that vt minus alpha squared vxx is equals to ut minus alpha squared uxx minus wt minus alpha squared wxx, right? So ut minus alpha squared uxx, where ut minus alpha squared uxx is equals to cosine 3t given in the problem. And then wt we can compute from here. Wt will be equals to alpha squared and wxx will be equals to 1, right? So we can plug the values in the equation, so it will become vt minus alpha squared vxx is equals to cosine 3t minus, for wt we can put alpha squared minus then alpha squared times wxx. So this will cancel out and we will left with vt minus alpha squared vxx is equals to cosine 3t, right? Now the boundary conditions are also homogeneous because we know that vx of 0 comma t will be equals to ux of 0 comma t minus wx of 0 comma t. That will make it 0, and again for vx of 1 comma t, wux of 1 comma t minus wx of 1 comma t will be 0. And then for v of x comma 0, we have u of x comma 0 minus w of x comma 0, right? So u of x comma 0 is given as cosine pi x plus half x squared minus x, and then minus w of x comma 0. We can see here that w of x comma 0 will be equals to x squared over 2 because this term will be 0, right? Then we will put t is equals to 0. That will become x squared over 2. So this term will cancel with this, and then we will left with cosine pi x minus x, right? Now this equation, we can again decompose this equation into two parts, and we will use Duhamel principle for one part and normal method for the second part. So we will split this equation. We can write it as, here we can divide the portion, and now here we will write v1. Yes, first of all we should write that now v of x comma t is equals to v of x, that is v1 of x plus v2 of x comma t, right? In fact it's x comma t. So now v1 equation for v1 will be v1t minus alpha squared v1 xx is equals to 0 with the homogeneous boundary conditions. v1 of x, let me write it again, till v1x 0 comma t will be equals to 0, and v1x 1 comma t is equals to 0, and then v1 of x comma 0 is equals to cosine pi x minus x. And for v2 it will be v2t minus alpha squared v2 xx is equals to cosine 3t. And similarly the boundary conditions will be 0 comma t is equals to 0, v2x 1 comma t is equals to 0, and then v2 of x comma 0 is equals to 0, right? Now we can see that this is a homogeneous equation with the homogeneous Newman boundary conditions, And this is a non-homogeneous equation with the homogeneous Newman boundary conditions. So we will solve this equation using Duhamel's principle. Duhamel's principle. And we already know the solution of this equation. We can say it 1 and we can say 2. So the solution of 1 is given by, from the previous lessons, we know that this solution is given by v1 of x comma t is equals to 1 over 2 times a naught plus summation n is equals to 1 to infinity cos n pi x times e to the power negative n squared pi squared alpha squared t, right? And the initial condition is v1 of x comma 0 is equals to this one. So we can write it as v1 of x comma 0 is equals to 1 over 2 a naught plus summation n is equals to 1 to infinity cosine n pi x is equals to cosine pi x minus x. Now we can see that this is a cosine Fourier series. So we know that the coefficients a naught is equals to 2 over L, that is 1, integral limit 0 to 1 cosine pi x minus x dx. So it will be sine pi x or x minus x squared over 2. Limit from 0 to 1, and we can see that this is sine pi x, so it will be 0 at 1 and 0 at 0, right? So this implies that 2 times 0 minus 1 over 2 and plus 0. Therefore, this is equals to negative 1. So a naught is equals to negative 1. All right. And then now we want to find n. So it will be 2 over 1, limit 0 to 1, cosine pi x minus x times cosine n pi x dx. So we can break the integral into two parts. So 0 to 1 cosine pi x times cosine n pi x dx minus limit 0 to 1 x cosine n pi x dx. All right. So it will be 2 times. Now we can write a formula for this to change it into the sum. So it will be cosine n pi minus pi x plus cosine n pi plus pi times x dx minus 0 to 1 x times cosine n pi x dx. All right, now from here we can see that this integral will be sine n pi minus pi times x or n pi minus pi plus sine n pi plus pi times x or n pi plus phi. Limit from 0 to 1. And this will be negative 2 times x sine n pi x over n pi plus this will be cosine sine and then again cosine n pi x over n squared pi squared. So sine n pi minus pi times 1, when we will apply the limits. So sine n pi minus pi, this will become 0 for both the limits, and this will also become 0 for both the limits. We will only left with this one. So this will be negative 2 times. When we will apply the limit to sine n pi x, so sine n pi will be 0, and for 0 again it will be 0. So only this is the function which will give the values for us. So this will be cosine n pi minus 1 divided by n squared pi squared. And we can write it as 2 over n squared pi squared times 1 minus negative 1 to the power n, because cosine n pi is equals to negative 1 to the power n. So we can see that if n is odd, this will be 4 over n squared pi squared, because this will be 1 plus 1. It will become 2. 2 times 2 is 4, and 0 if n is even, right? So now we can write the value will be 4 over n squared pi squared for this integral. So an is equals to this. And we already got a naught, that is negative 1. Now we can write that v1 of x comma t is equals to negative 1 over 2 plus summation n is equals to 1 to infinity 4 over n squared pi squared cosine n pi x times e to the power negative n squared pi squared alpha squared t. So we are done with v1, and now we are going to work on v2. So for v2, we know that equation is v2t minus v2xx alpha squared is equals to cosine 3t. Now using Duhamel's principle, v of x comma t such that s will be equals to cosine 3s. Right, for t we'll write s. Then therefore v is equals to integral 0 to t cosine 3s times ds. This will be equals to sine 3s divided by 3 from 0 to t. Therefore, the solution is equals to sine 3t over 3. So v2x comma t is equals to 1 over 3 times sine 3t. Now we are done with v1 and v2. So v of x comma t is equals to v1, that is -1/2 plus summation n is equals to 1 to infinity 4/n² pi squared cosine n pi x e to the power -n² pi squared alpha squared t plus 1/3 times sine 3t. So the general solution will be u of x comma t is equals to v of x comma t plus w of x comma t. So now u x comma t is equals to -1/2 plus summation n1 to infinity 4/n² pi squared cosine n pi x e to the power -n² pi squared alpha squared t plus 1/3 sine 3t and w of xt, that is plus 1/2 x squared plus alpha squared t. So this is the final answer. All right, so we can verify this solution by applying the boundary conditions and by using the initial conditions as well, right? If you want to apply the boundary conditions, first of all, we need to find ux. Then we will apply the conditions, that is ux of 0 comma t is equals to 0 and ux of 1 comma t is equals to 1, right? And then we will verify that the solution gives this value or not, right? So you can verify, and also you can verify the initial condition as well, right? At x comma 0. So this is the idea of Duhamel's principle. Thanks for watching the lesson.